Okay, so what I'm going to introduce now is another tool for model selection. This is validation curves. So what we are essentially asking here is it possible to plot the optimal hyperparameters? So it really is. And in order to show you what I mean by plotting the optimal hyperparameters, I'm going to show you this example here. So what I'm importing here is validation curve from model selection in scikit-learn. And then a bit similar to before, I create an output that's train scores and test scores. So here I use validation curve that I just imported here. And again, I use this pipe lasso from one of the previous videos. I specify again that my data is the development data. And what I'm going to do now is basically that I'm going to estimate or train my model, train a model, a lasso model for different lambdas. So a bit similar to what I did in one of the previous videos. What I'm going to use is a scoring measure in order to evaluate the performances of all these different models with different hyperparameters is the negative mean square error, and I'm using tenfold cross validation as I also did in the previous video. So what I'm doing then is that for each of these models that are estimated with different lambdas, I create a data frame that I call MSE score using the pandas data frame class constructor, and I create a column that's called train, which is minus the mean of the performance measure on our training data. So again, I'm using tenfold cross validation, right? So that's why I compute a mean, and I'm using minus because what I had up here was the negative of the mean square error. So then we're essentially back at something that's like the mean square error. And then what I do down here is basically just a similar thing, just for the scores and the test data set. And then what I have here is the lambdas, and I set the index to be the lambdas. So what I can do now is that I can print the score I can print the lambda that's associated with the lowest score in this mean square error measure. So that's in this case this lambda here, and the score that's associated with that is the following thing here. So that's also what I'm plotting in this case. So you can see here for low lambdas, then we have that the performance on our training data was very good. So that's basically because we had overfitting, while the performance on our validation data was not as good, right? So what we can see now when we increase our lambda, so we are penalizing high coefficients more, basically, or we are to a larger degree penalizing coefficients that are different from zero, basically. Then the mean square error on our validation data, it drops a bit, while the mean square error on our training data, it increases quite dramatically here. So what you know is that we are essentially interested in lambda that obtains the lowest mean square error on our validation data. So you can see that's probably around here, right? And what we can also see is that the curve here is fairly smooth. So the fact that this is the best performance here, that we obtain the best performance for this lambda, it doesn't seem very random. If we had a curve that jumped like that, it could be the best performance could basically have been anything, right? But this, I think, this adds credibility to this hyperparameter, this optimal hyperparameter, that the shape of this curve here is quite smooth and just seems to decline just a tiny bit here. Okay, and we can also see that the performance on both our training data set and our validation data set is just horrible for high lambda. So I guess in these cases, the large degree of penalization just ensures that all coefficients are basically just zero, and we just get a horrible estimate here.